In this second semester, I shall be dealing with the second course of T.Y.B.Sc Physics, namely PH 342, and name of the course is Quantum Mechanics. So we already know what classical physics is. Classical physics or Newtonian mechanics, which is 19th century physics, which was mainly developed by Newton and hence called as Newtonian mechanics. It was also developed by authors like Lagrange, Hamilton, D'Alembert, and so on. So classical mechanics is a study of motion of objects where the classical laws or laws framed by these pioneers, they are applicable. In 19th century physics means from the period 1800 to 1900, which we call as a 19th century physics, Newtonian mechanics was there, as well as classical electromagnetic theory was also developed by Maxwell, and people were knowing the phenomenon like interference. So light possesses wave nature, which was confirmed from the interference experiment. So when we say 19th century physics or classical theory, then it is Newtonian mechanics or classical mechanics, as well as classical electromagnetic theory and wave nature of light. Then these classical ideas completely failed at the turn of 20th century. Therefore, our first article is the origin of quantum theory. Chapter 1. Origin of quantum theory. All the ideas which were there in a classical theory, they failed in some of the experiments which we are going to discuss. So the first article that we are going to discuss is failure of classical ideas. Failure of classical ideas. And one of the very few things that classical theory could not explain was the nature of energy in the spectrum of radiation emitted from a black body. So our first experiment, which will be treated as the first failure of classical theory, is black body radiation. Black body radiation. Black body radiation. As I already said, one of the very few things that classical theory could not explain is the black body radiation. A perfectly black body is defined as one which absorbs all the radiations which are incident on it, corresponding to all the wavelengths. In practice, the name black body is appropriate because it doesn't reflect any light and absorb all the wavelengths or all the radiations corresponding to all the wavelengths. In practice, we don't have perfectly black body, or in practice, we don't have ideal black body. But a nearly black body can be constructed by taking a hollow cavity or an enclosure which is coated with diffuse layer of black pigment such as lamp black, and which has a small aperture through which the radiations can be admitted. So here is an example of a cavity or a black body. So you can have any shape for black body, and it has a small aperture from which radiations from outside can be admitted. The inner side of this particular body, inner wall of this particular body is coated with diffuse layer of lamp black, and it suffers multiple reflection, and that particular wavelength or that particular color gets completely absorbed in a nearly black body. If this particular body is heated, then it emits all the colors, all the wavelengths, all types of wavelengths, and the spectral distribution of the radiation within the enclosure is continuous in nature. And this these radiations which are continuous in nature, they depend totally on shape, doesn't depend on shape of the enclosure or cavity as well as material of the cavity, but is a function of temperature alone. So as you will go on increasing the temperature, the spectral distribution of radiation within the enclosure will go on changing, but it will remain continuous. So such a type of radiation within a uniform temperature enclosure are called as black body radiation, and perfectly black body is one which absorbs all the radiations as well as emits all the radiations. What I am going to discuss now is the experimental fact or truth, which I mean the experimental observations of a black body radiation. So here are the experimental curves which are obtained for a black body. What I am plotting here is U lambda, intensity of radiation emitted from black body as a function of lambda at various temperatures. If I take a constant temperature such as 1000 Kelvin, 1000 degrees Kelvin, then the curve is of this particular kind. This is our first experimental curve which was obtained at 1000 Kelvin. Okay. Then if you raise the temperature, then curve has this particular shape. This is at T2, which is 1200 degrees Kelvin, and then if you still raise the temperature, then curve is of this kind and is T3 at 1500 degrees Kelvin. So these are the experimental curves obtained from black body radiation curves. What we observe here, what is plotted on vertical axis is U lambda, intensity of radiation. Intensity of radiation is defined as energy per unit area per unit time emitted from a black body in the wavelength range lambda and lambda plus d lambda has been plotted as a function of a lambda at various temperatures, and temperatures are 1000, 1200 and 1500 Kelvin. So what you observe here is at a given temperature such as 1000 degrees Kelvin, what you observe is the intensity goes on increasing with increase in wavelength, reaches to certain maximum at lambda max, and then again decreases with increase in wavelength. So for the first curve, this is lambda max 1. It is not a maximum wavelength, it is wavelength at which maximum in intensity is obtained. What is lambda max? It is the wavelength at which maximum in intensity is obtained. It's not a maximum wavelength. So for a given temperature, the intensity of a radiation goes on increasing, reaches to maximum at lambda max, and then again decreases with increase in intensity. So similarly, what you observe here is this as a lambda max 2, and this is lambda max 3, For all temperatures, the intensity goes on increasing, for all temperatures. For the entire wavelength range, the intensity goes on increasing. But what you observe here is with increase in temperature, the lambda max is decreasing. Lambda max is decreasing. And for every curve, the product, namely lambda max into temperature, remains constant. For every curve, this remains constant. This is very crucial relationship, and which is the origin of how the Planck's constant H, the universal constant of nature, was discovered. So these are the experimental curves, and we want theory to explain this curve. So classical people have made various attempts using classical theory to explain this particular curve. Significant contributions were made by Wien and Rayleigh and Jeans. Wien and Rayleigh and Jeans. So people have tried to put forth theory on the basis of classical theory which they were knowing in the 19th century. So what Wien did is that he treated the particles of the wall of the black body as a simple harmonic oscillator. He treated the vibrating particles as a simple harmonic oscillator, and using classical electromagnetic theory, he deduced this particular formula. U lambda d lambda. What is U lambda d lambda? It is energy emitted in wavelength range or region lambda and lambda plus d lambda. Energy emitted in wavelength range lambda and lambda plus d lambda is A upon lambda raised to 5 e raised to minus b by lambda t d lambda. This is our first equation. This is Wien's law. This is Wien's law, which was derived on the basis of classical physics by making the use of the particles, vibrating particles of the wall of the container as if they are harmonic oscillator and electromagnetic theory. This particular formula was in good agreement with experimental curves only in a small wavelength region. So this particular formula could explain only this particular part, small wavelength behavior. It could not explain it was not applicable for long wavelength region. Then Rayleigh and Jean, they came forward and they have suggested theory to explain these experimental curves. What Rayleigh and Jean does is that they have applied classical law of equipartition of energy, assuming that each particle will be treated as a harmonic oscillator, and each oscillator of molecular size will have average energy kT. Each oscillator will have average energy kT. This is equipartition theorem. By making use of this equipartition theorem, Rayleigh and Jean derived this particular formula, U lambda d lambda equal to 8 pi kT upon lambda raised to 4 d lambda. Equation number 2. This is Rayleigh and Jean's law. This is Wien's law. Wien's law, which was applicable only in a small wavelength region. And this is Rayleigh-Jean's law. This law was in agreement with these experimental curves only for long wavelength behavior. So this formula could explain only long wavelength behavior of these black body radiation curves. So it could explain only this particular part, and it could not explain the low wavelength behavior. Remember, Wien's law is applicable only in a small wavelength region. It's not applicable in long wavelength region. And Rayleigh and Jean's law explains or describes only long wavelength behavior, and it cannot be applied for a small wavelength region. So there was no single formula to explain these entire radiation curves over the entire wavelength range, and therefore all attempts to obtain a single formula which could explain the behavior of all these radiation curves over entire wavelength range failed completely, and there was no single formula for explanation of these black body radiation curves. So this is the first failure of classical theory. Next time we will discuss photoelectric effect, where classical theory again failed to explain the experimental observations of photoelectric effect. Thank you.